Assalamu alaikum everyone. This is digital control system. We are discussing chapter 2, the Z transform. So we started first class with some of the definitions of Z transformation, and then we have seen some examples of Z transformation, basically on some elementary functions. Now today I will look into some important properties and theorems of the Z transformation. And before going to that, I want to cover some of the topic related to the definition of the Z transformation from some other book. That will be actually will help us to understand the Z transform or Z transformation even better. So let's see what is the definition given. It says that given the causal sequence so we have a causal sequence given, and the Z transformation is defined as uz equal to u0 plus u1 z to the power minus 1 plus u2 z to the power minus 2 plus goes on to uk z to the power minus k. Okay, so essentially it is the same thing as k equal to 0 to infinity uk z to the power minus k. So one-sided z transform or unilateral z transform. Okay, so same definition, but it is given for a causal sequence. Causal sequence is simply refers to a sequence that starts from time 0 and for future times. So there will be no data for past values. Okay, so this is what is causal sequence. So this is definition 1 according to that book. The name of the book is Digital Control Engineering. Let me give you the reference as well. Digital Control Engineering. The author is M. Sami Fedali. M. Sami Fedali. Okay, so this book also seems a bit well written, and also it is one of the recent books. So some of the topics has been covered very well in association with the time change. Okay, so this is the definition 1. Definition 1. In terms of a series, if a series is given, then how to find out the Z transformation of that series. So basically it depends on coefficient at time 0. Then after a time delay, say t, ut, u1, then another time delay. So goes on. So similar idea eventually, but it is a different perspective to see how to represent the Z transformation. So this is for a causal sequence, definition 1, according to that book. And the second definition is impulse. If we have an impulse train representation of a discrete signal, say we have a discrete signal which is represented by u star t equal to u0 del t plus u1 del t minus capital T plus u2 del t minus twice capital T. Okay, so it continues until uk del t minus k capital T. Okay. So if this is the scenario, this is a impulse train representation of a discrete time signal. So if this is impulse train representation of a discrete time signal, so what will be the Z transformation of this signal? So to find out the Z transformation, the definition says we have to take the Laplace transformation. Laplace transformation, and that gives us u star s equal to u0, then u1. Basically, the time delay is represented in the Laplace as e to the power minus st. Similarly, u2 e to the power minus twice st plus goes on up to uk e to the power minus k st. Okay, so if we write in a summation form, so then we have is summation of k equal to 0 to infinity uk. Then you have e to the power minus kst. Now we can actually rearrange this one a bit in a way that k2 summation of k goes to 0 to infinity uk, because we have to have the k to the power minus k, so we can write est to the power minus k. So now if we let this parameter to be our z, then we can say that k equal to 0 to infinity uk z to the power minus k. Okay, so this is second definition. So in every time instant, basically this is at t equal to 0, then this is t minus t, t minus twice t. So every time instant, we're actually taking a unit impulse function with a delayed version. Ultimately, this is t minus t, this is t minus twice t, and then this is t minus kt. Okay, so if this is the scenario, then with the assumption that z e to the power st can be replaced by z, this is your definition 2 of your Z transformation according to that digital control system engineering book. So now why I was actually getting interested about it is sometimes the train of pulses will be provided Based on that, we can actually may have to generate the uh, Z transformation. So one of the example says that if you have a series UK, don't worry, U in our book, the textbook, U is basically X. So we are just using U instead of X. So if you want, you can also write XK, no problem with that. So we have a series of pulse, they are saying, from K equal to 0 to infinity. And the pulses are something like this: 1, 3, 2, then 0, 4, then it continues as a 0. Okay, so if this is a pulse, then they're asking us to find out what will be UZ. Okay, so this is what we have to do. So we know that this is for t equal to at instant t. This is for t minus t. If it is time sample, but if it is not time sample, then it is actually k equal to 0, 1, 2, 3. So this is how it is. So what is the unit Z? What is the Z transformation of this one? Very simple. So first instant will be as it is, because Z to the power 0 is 1. So plus 3. This is actually U1, sorry, U0, U1, U2, U3, U4. Okay, so it goes on. So second will be Z to the power minus 1, then third one will be Z to the power minus 2, then fourth one will be Z to the power minus 3. So since multiplying with the 0, it will be vanished. So basically 4 into Z to the power minus 4. So rest of the parameter doesn't count because the rest of them are 0. So this is our corresponding Z transformation of the pulse that is being provided. Okay, so sometimes if the pulses are given, so in this way, we can actually easily find out what will be the solution of our Z transformation. Now, the identities that we are using in our book, but they haven't mentioned this particular book, Control System Engineering, they mentioned. So the identities, two identities that we are using. So they are actually, number one is summation of k equal to 0 to infinity, ak, a series, infinite series, ak is infinite series. And the summation is basically 1 plus a to the power, sorry, 1 minus a to the power n plus 1 divided by 1 minus a. If your a is not equal to 1, and the other one, which one more commonly used, is k tends to 0 to infinity, ak, infinite series, is 1 by 1 minus a. Okay. So, and this is true only for a in the magnitude of a is lesser than 1. So basically the common ratio, if it is lesser than 1. So in other day, we actually said that the value of r has to be, the value of r has to be, the common ratio has to be lesser than 1. So similar thing in a different book, they have used different notation. And sometimes this parameter can be your first parameter. So we have said something like this, a by 1 minus r. So this can also be the scenario where your magnitude of r has to be lesser than 1. So then it will actually converge to that particular value. Okay, so in the last class, we have find out the solution of unit Z transformation of unit step, exponential, and all that. So one of them which was left was basically the impulse response. So if you have a unit impulse, and if you want to have a Z transformation of that one, then what should be the value? So Z transform form of unit impulse signal, okay. So the definition one will be handy here. So UK or XK, whatever you write, is equal to del K. Okay, so K can also have T. T can have a magnitude of 1 second. So ultimately same thing. So this is the definition one for K equal to 0, and for some other value, the magnitude of K magnitude is 0 for any other value which is not equal to 0. So if you want to see graphically what it means is basically we have a pulse. We have a pulse train, something like that, magnitude 1 at 0, and some other parameters like 1, 2, 3. If you don't want to take the other side, then only so the rest of the values are actually 0. So if this is the scenario, then what should be the value? Now, if you take the first definition, what the first definition says is basically rest of the magnitude is 0, isn't it? So first definition is u0 plus u1 z to the power minus 1 plus u2 z to the power minus 2 goes on, continues like that. So we only have one magnitude, the rest of them are 0, and this is a magnitude 1. So that is why. So xz or z transformation of your delta function is actually 1. So very simple definition wise, you just figure it. Otherwise, it is difficult to find out the uh, Laplace transformation of delta function with a limit of 0 minus to 0 plus, and doing some complex manipulation and then figuring out. But if you take the first definition, it is relatively easier to do. Similar thing can also be shown taking the advantage of the definition one in case of your unit step response as well. Unit step signal if you want to find out the Z transformation of this one. So the pulses actually also help us. So if we can figure out the pulses at say k equal to 0, then k equal to 1, k equal to 2, k equal to 3, goes on, continues like this. So we can actually write xz equal to simply the first value, always the constant is 1 plus 1 into z to the power minus 1 plus 1 into z to the power minus 2 plus 1 into z to the power minus 3 continues up to 1 into z to the power minus k. So you can easily find out the series. And now with the condition that the common ratio R is basically lesser than 1, we can easily find out its solution 1 by 1 minus j inverse. Okay, so 1 in general comes as a common factor, but sometimes it can have some other value, the first parameter. So this definition is actually somehow gives a better view or better understanding of the Z transformation. Okay, similar. Okay, now let us come to the properties of the Z transformation. So one of the common properties is multiplication with a constant. So it's actually simple, which can also be included inside the linearity properties. So important properties and theorems of the Z transform. So this is article, I think, 2.4. Okay, so few important properties are there, and we'll try to understand them. So first one is multiplication by a constant. So if we have multiplication, first one. So if the Z transformation of xt, so xt's Z transformation is xz, then what will be the case that is Z transformation of a xt. Okay, so multiplying just by arbitrary constant, so it will be simply a z xt equal to simply a xz. So very simple thing. So actually it doesn't need proof. You can just see it by example that. So, but still in the book, a small proof is given. So it's up to you. You can have a look at that one. So second one is linearity property. So linearity property. So if you have homogeneity, okay. So uh, if you have two functions, say alpha f1 t plus beta f2 t. So if these two functions is there, then what should be its corresponding Z transformation? As you can see, there's two things. One is two functions is added. So you can have two separate sources and you can apply those two. And if you apply those two separately, then whatever the solution you're going to get, and if you add those two, then you will also get the similar, the summation of the individual Z transform. This is what about the linearity properties as well as the multiplicity, as you can see. So scaling is one thing, which is the multiplicity, and also homogeneity. So that is different inputs have different responses. So if the inputs are summed together, so the responses can also be summed together. Okay, so it should give us alpha f z f1z plus beta f2z. Okay, so again, definition, derivation you can go through, but it's not that complicated. So it's up to you. Just have a look at that one from our textbook. So these two are covering from the Ogata books. So you go into that one. Now, one example of the linearity we have to see, that is from control system in digital control engineering book. Okay, so say xk is our signal, and which is a pattern like this, 2 into 1k plus 4 into del k. Okay, so and k ranges from 0 to infinity. So if this is a scenario, so what should be the value of the Z transform? So xz is, what is the value of that one? We have to figure it out. Okay, so now it's just apply the linearity theorem. So linearity theorem said the Z transformation of 2 into 1k plus 4 into del k is simply, you take the coefficients out, then you just apply this value. Just wait for a minute. I have an emergency incident. Okay, so take the first one, and then you isolate the second one, the coefficient of the second one, then apply the Z transformation of del K. So by, 1K is nothing but unit step, and del K is nothing but your impulse. Okay, so both of them are sampled. So we can apply simply the formula that we have learned, derived in the last class. Also, your table 2.1 will be also provided, so you don't have to bother about that one too much. So according to the formula, you can have Z by Z minus 1. And we have only the Z transformation of del is 1, so just simply 1. So what we have is twice Z divided by Z minus 1 plus 4. So simplify a bit, Z minus 1 twice Z plus 4Z minus 4. So 6Z minus 4. 6Z minus 4 divided by Z minus 1. So this is your corresponding Z transformation. So we can see that linearity theorem actually works with the Z transformation. Next is multiplication by the exponential. So basically what is meant by multiplication by AK. So this is also from Ogata book. So what it means is Z transformation of xt equal to xz. If this is the case, then Z transformation of AK times xt will be actually, according to what they're saying, is x a minus z. Okay, what it means is wherever in your transformation you have z, that will be actually replaced by az. So you have a function, say z transformation of unit step. So z transformation of 1t is basically 1 by 1 minus z inverse, or actually you have z by z minus 1. Okay, so now z transformation of AK times 1t, if this is a scenario, then if you take the first example, so 1 minus A inverse Z. So this will be the case. Okay, so wherever you have Z, Z will be just simply replaced by your new variable, that is A minus Z. So this is what is all about this theorem. So let's go for the proof of this one. Application we have just seen, and the proof is Z transformation of AK xk equal to Z transformation of, we can write simply the summation of k equal to 0 to infinity, then AK, then you have xk z to the power minus k by definition. So this is your function as it is z to the power minus k. Now we can actually take common of the parameter here. K can be taken common of. So x k z a minus z to the power minus k. Is it okay? So by definition, Z transformation XZ is basically summation of k equal to 0 to infinity xt or xkt. Then you have z to the power minus k. So wherever here you don't have any z, so only you have z here. So that z actually goes into inside the function. So similarly, whatever the parameter here, which is under your, which is the base of your z minus k to the power minus k. So that thing will be going into your function. So x to into x function of a to the power minus 1 z. Okay, so they have taken this example. That is why you have a response something like that. But the other book, they actually have multiplied the function with e to the power minus k. So you can also do that multiplication with minus k's. And now if you do that, so then the transformation will give you x az simply. Is it okay? Because you have minus k here, and also in the function of the z transformation, you have minus k. So minus, you can easily take common of ak. Ak will be base, so you can also have this one. So it's up to you. You can use this one, or also you can apply this one. Okay, so next is if you have a shifting theorem, then well, how can we deal with that one? So I think this one and the third one. Now we're going to the fourth one. Fourth one is shifting theorem. Basically, time shifting we're talking here, time shifting. And there is two ways. One is time delay, and another is time advance. Okay, so time delay is if you have this is your t equal to 0, then this is your t minus k, sorry, t minus t, then t minus twice t. So this is the time delay. Time delay. Or also it's in some books you'll find it's called right shift. Okay. And the other one, if t equal to 0 is this, so you're moving this one is your time advance. And this is wrong delay, I mean, sorry, left shift. Okay, so there is two theorem associated to this one, and how this thing works is derivation itself is a bit involved, as well as the understanding. So how can we derive this one? First question. And secondly, how can we go about implementing that one? Okay, so okay, let us go with time delay first. So if again the same theorem, same initial conditions, z transformation of xt, if this gives you xz, then z transformation of a delayed signal by any parameter nt, or simply you can write also k minus n. So it's up to you which one you prefer. So either you can write t minus kt shifted. This is one way, or you can also write the shift of x, sorry, and this should be n shifted by n amount, or k minus n simply. So this is for the sampled one, time function. This is for you number sequence. Okay, so let's and okay, so what is the shift? It says z to the power minus n, then whatever your function was. So this is your definition of shifting. Similar thing. Okay, that's z to the power minus n x. Okay, so let us try to derive this one. Say z transformation of x k minus nt equal to, according to the definition, what we have is k summation of k equal to 0 to infinity. Then x, k can be replaced. Okay, sorry, we are taking the first one, so we have to take t here. Okay, so t minus nt. So t can be replaced by kt minus nt. Then z to the power minus k. Now what we know here is we should have something like this. So by definition of z transformation, k equal to 0 to infinity x kt, then z to the power minus k. So whatever we have here, we should also have the same k here. So now what is the scenario here is k equal to 0 to infinity is x, basically what we have k minus nt. So in the power of z, we also have to bring that one minus k plus n minus n. So equal to 0 to infinity xk minus nt z minus k minus n z to the power minus n. So we can bring the z to the power minus n to the font, k equal to 0 to infinity x k minus n t z to the power minus k n. Okay, so now we already have this portion. Okay, now this one we just have to write as xz. So to write xz, what we have to do is all the parameters should be started. K should be started from 0 to infinity. This range should be from there, as well as this parameter has to be a function of this one. What I mean is, as you can see here, k equal to 0 to infinity, then x kt, so z to the power minus k. So it has k here, and also range is in the k. But here, as you can see, they are not only k. So somehow we have to come back to this one again. Then we can write this is equal to xz. So for that, what we can assume that m equal to k minus n. So what does it mean is when k equal to 0, we can say that m equal to is basically minus n. So applying this condition into that equation, what we are going to get is z transformation of xt minus nt equal to z to the power minus 1. Then range is now from m equal to minus n to infinity. Then x mt, replacing the values only. And then you have z to the power minus n. The only problem here is that range is not from 0 to infinity, so rather it starts from some negative value. But it doesn't bother us too much because of the fact that we know that the value of m, t, is only having values, some valid values, if t is greater or like if m is greater or equal to mt, or basically t is smaller t is greater or equal to 0. And if mt or simply the smaller t is having 0 values if the value of the t is smaller than 0. In this case, mt is smaller than 0. So we can easily simply write z to the power minus 1 summation of m to the 0 to infinity, because the rest of the parameter, those are negative, will be eventually, the magnitude will be 0. So x mt z to the power minus m. Okay, so few things we need to correct. Okay, so now we can simply write that this is nothing but z to the power minus n xz. This is the z transformation, a time delayed signal. Okay, so what does it mean? That if you have a signal 1t, okay, and the z transformation of this one is 1 minus 1 minus z inverse, then z transformation of 1 t minus 4t, what should be the z transformation of this one? So fourth value is being shifted by fourth time sample. So basically z to the power minus 4, then the same function z transformation of 1t, and that is z to the power minus 4, 1 by 1 minus z inverse. So this is your answer. So time shifting, basically time delaying, is a lot easier compared to the time advance. Let us now try to derive the time advance thing. Now, let us first define the theorem, then try to derive it. And deriving may at times become a bit complicated. So we can go with the derivation with the Ogata book, or we can also go with the derivation of the other book, Digital Control Engineering. So let us see what does it actually means. If you have a signal, say xk, we want to see what will be the z transformation of xk plus 1. So let us try to derive it first with simple one. So z transformation of xk plus 1 is basically, according to the definition, summation k tends to 0 to infinity, x k plus 1 z to the power minus k. Okay, so what we need here is whatever, again, same idea. K values has to be same. So what you can write here is summation of k equal to 0 to infinity, then x k plus 1, z to the power minus k minus 1 plus 1. So basically, k equal to 0 to infinity, x k plus 1, z to the power minus k plus 1, then z will be simply there. So that z we can take to the front as before, z, then summation of k equal to 0 to infinity. Okay. And what we have is x k plus 1, z to the minus k plus 1. So again, we have to check with the limit. And what we can say is the limit has to be m, and say m equal to k plus 1. Now, problem is if k equal to 0, m is giving us 1. So our series is not starting from basically 0, rather it's starting from the value magnitude 1. Okay, so what you can write is z, then summation of m equal to 1 to infinity, then it goes with xm, then z to the power minus m. So now actually you have to bring one parameter, you have to add one parameter with this one, otherwise we cannot write the z transformation. So what we have to do here is z, so m equal to 1 to infinity xm z to the power minus m. So we have to add the first parameter, that is x0. Okay, so if we add x0, because at m equal to 0, z to the power 0 minus 0 is actually 1, so x0 is missing only. So we're just adding that parameter, and then we also have to subtract that one. So now this one can be added with this one, and we can find the range that is we can find the range that is from m equal to 0 to infinity xm z to the power minus m minus x0. So now what we have is z, and now we can write this one as a xz minus z x to the power. So one of the initial value has to be subtracted. So this gives you z transformation of a positive, time advanced signal. So x k plus 1. Now k plus 2 also you can see for a better understanding. So I'm leaving it to you, that is z transformation of x k plus 2. So it's your task, try to do that and find out all other parameters that you should be including here. Okay, so now let us go to the derivation of your Ogata book, where they are actually giving a common formula. If nth time advance is there, z to the power x k plus n, nth time advance. In that case, they are saying that the derivation will be, the formula will be z to the power n xz minus k equal to 0 to n minus 1 x kt z to the power minus k. Okay, so actually in your Ogata book, they are actually using the time function for derivation. So instead of k and n, they are actually using t minus t plus nt. Okay. So interchangeably, you can actually also go for the number sequence. So there is no problem with that one. So let us try to see the derivation. So there's a transformation of x t minus t plus nt, since time advance is equal to summation of k equal to 0 to infinity x kt plus nt z to the power minus k. So similar idea, I'm just going very quickly. So actually you should give two bracket here. It will be more appropriate, plus k plus n, then t, z to the power minus k, it should be plus minus n plus n. Okay. So k equal to 0 to infinity x k plus m t z to the power minus k plus n, then the other z to the power n can be taken to the front. Okay, again, same idea. What we can say that m equal to k plus n, and now if k equal to 0, then m equal to actually n. So we are starting from m. So if we place those values to the power n, summation of k equal should be m, m equal to n to infinity. Then you have x mt z to the power minus n. Okay. So what we need here is we have to add the parameters and also we have to subtract the parameters. So since z to the power n is already there, we just can take the summation of m equal to n to infinity x mt z to the power minus m. With that, we have to add the value that is from m equal to 0 to, already we have n to infinity, so n minus 1. Okay, so n minus 1 x mt z to the power minus n. Also, you have to subtract that one, so m equal to 0 to n minus 1, then x mt z to the power minus n. Is it okay? So now these two can be added together and we can have the range from 0 to infinity. So z to the power minus z to the power n, summation of n equal to m equal to 0 to infinity x mt z to the power minus m minus m equal to 0 to n minus 1 x mt z to the power minus m. Okay, so what we have is this one can be replaced by x z. So z to the power n xz minus m equal to 0 to n minus 1 xkt xmt z to the power minus n. Okay, so as you can see, this is only just normal parameters of x and z. Only the thing is instead of the range is from 0 to n minus 1. So you can keep the m, or m can be replaced by k because they're just counting the values from 0 to n minus 1. So you can just change that one. So that will give you the derived version. So ultimately same thing. So this is the derivation for the time advance. So time advance is a bit complicated at times because you also have to find out the initial values and you have to subtract those as well. Okay, so let us look at one example of this one. So xk, the series is given, that is 4, 8, 16, goes on. So this is your causal sequence. If causal sequence is given, then how can we figure out the values? So we can write xk as an expression of 2 to the power k plus 2. So as you can see, if k equal to 0, 2 to the power 2 is 4, k equal to 1, 2 to the power 3 is 8, k equal to 2, then 2 to the power 4 is 16. So it can easily represent this system where k equal to actually 0, 1, 2 goes on. Okay, now we can say that fk, we're just taking that fk equal to 2 to the power k. Okay, and we already know the formula for xk. Okay, now if we have to find out the z transformation of xz, then what we have actually it is 2 times shifted. So we can write that this is as a, if we assume this one, then we can say this is actually f into f as a function of k plus 2, 2 shifted. So if it is the assumed fk equal to twice k, then we can say that fk plus 2 will be simply 2k plus 2. Is it okay? So now what we can say is that this is shifted by 2 unit. So that is why it will be z square. Then you have that formula that we have derived. Now that will give you is fz minus z square f0 minus z f1. Okay, so how this one is coming? So from this one, say this is for nth, this is for your z transformation of nth advance x t plus nt. So now if n equal to 2, then what we'll have is z to the z square into xz. So the function as it is minus, now n is value is 2. So the first parameter will be there. So first parameter, our range will be from 0 and 1, 2 minus 1. So first parameter of this one is basically x0, z to the power 0 is 1, and the second parameter is basically x1, then z to the power minus 1. So since we are multiplying with z squared, so basically it will be z square xz minus z square x0 minus z x1. So whatever the initial condition x0, x1, we have to know, then we have to multiply with z square and z correspondingly. So depending on the number of the time advance, you have to actually find out, expand the series, and you need to figure out. So in this particular case, we have a 2, so we have just expanded in that way, and we have to also calculate what is the value of your f0 and f1. So f0, now what we are assumed from here, we can easily find out f0 if 2 to the power 0 is 1, and f1 is 2 to the power 2 is basically 2 to the power 0 is 1, and 2 to the power 1 is 2. So these are the two values that you can get. And the now also if k is ak, then we know that the derivation of this one is fz is basically 1 minus 1 by 1 minus a inverse z. Is it okay? So, and if you just do it, and also you have a minus, so ultimately what we are going to get 1 by 1 minus a z inverse. Or another way to represent this one is if you just multiply with z in the numerator and the denominator, z by z minus a. So z by z minus a, and in our case a is basically 2. So 2 to the power k. So what we are going to get from here is, in our particular case, is z divided by z minus 2. So just apply those z square from the formula, then z by z minus 2, then z square from the formula, then f0 we calculated is 1, and z, then f1 is calculated as 2. So simply z cube by z minus 2 minus z square minus twice z. Now, if we just do a bit of simplification, z minus 2 and z cube minus z square z minus 2 minus twice z, z minus 2. And it should give you z cube minus z cube minus basically plus 2z square minus 2z square plus 4. 4 2z, basically 4z. So z minus 2. Now this cancel. Whatever left is basically 4z by z minus 2. So this is our solution of your time advance equation. But this is not only way to solve this one. You can also solve it using another alternative manner, like xk say is something like this, 4, 8, 16. So you can easily take common of 4 of this one. So you can have something like this, 4, 1, 2, 4. Now you can easily write 4 into the power k. So this is your multiplying by constant formula. So you can also use that one, which is a lot simpler than the previous one. It is basically 4 z transformation of 2 to the power k, and which is nothing but 4 z by z minus a, which is z by 2. So 4z by z minus 2. Simple way to solve this one. So a particular problem can be solved in a different ways. So I think we have gone through a lot in this particular class. Also, few other shifting theorem. If you want, you can actually go about. Some other example is also there in the book. So I would rather want you to explore those. So from the Ogata book, example 2.3, 2.4, 2.5. So you try to have a look at that. Those are relatively simple. Then actually 2.2 and 4.5 is a bit interesting. So let's see whether very quickly we can solve it. Example 2.5. Yk is given as a summation of k equal to 0 to infinity x of h, and k equal to 0, 1, 2 goes on. So this is the scenario, and you have to, and also yk, just like a causal sequence, 0 for k smaller than 0. So we have to find out what is yz. Okay, so let us try to solve it. So the sequence yk can be written as, if we expand it, x0 plus x1 plus x2 goes on up to x k plus k minus 1 and then xk finally. Now y k minus 1 can be written as one less parameter. So basically the same thing with one less parameter. So x k minus 1. So now if we subtract the second one from the first one, what we are going to get is yk minus yk minus 1 only will be the last parameter xk. So if we take z transformation in the both side, so we apply z transformation in the both side, linearity formula property will be applied in this side. Okay, so what we are going to get here is, this is simply z transformation of yk, so yz, and this is a delayed version. So z to the delayed by 1, so z to the power minus 1 yz equal to xz. Okay, so now 1 minus z inverse yz equal to your xz. So we want to find out yz equal to 1 by 1 minus z inverse xz. So this is your required solution. So we are taking the advantage of the series, taking the advantage of time delay property as well as linearity property to find out the Z transformation of an infinite series. So these tricks will be more and more comfortable to you once you actually practice more and more. So still a few properties are left, but I think it's almost 1 hour or slightly more. So let me stop here in this class and we'll continue from this one, and then also inverse Z transformation in the next class, inshallah.